Hello, I'm Michael Littlecrow, and this video is going to explain Descartes' Rule of Signs, which comes from Pre-Calculus Math 170 and section 2.5 of our current textbook. So the Descartes' Rule of Sign will tell us how many possible zeros there are for a polynomial function. It doesn't tell us how to find them. It only tells us the existence of how many. So there's two different steps to it. The first step tells us how many positive zeros there are, and the potential of how many negative zeros there are is by the second step. But then once we have the number, the possible potential numbers, as we will see, by counting the sign changing, we will then need to use the rational zero theorem to actually find them. And the possible rational zeros occur at the ratio of the factors of the constant term. So the last one, that's the term without any integer or any variable there, divided by the factors of the leading coefficient, which is the coefficient in front of the term with the largest degree, the largest exponent. So we'll take a look at how we do that, but first we'll apply Descartes' Rule of Signs. So while we're here to find the positive real zeros, we just count the sign changes. So what they've got as their example is we start with a positive in front of the 3x to the 7th, and then it changes. The next term has a negative, so that's a sign change. When we go from this negative, this subtraction here, we go to the next term, we've got two negatives, so that is not a sign change. We go from this negative here to this negative, or sorry, to this positive, keep track. That is a sign change. We went from negative to positive, so we're going to count that as our second sign change. So this is the first. This is the second. And then we go from positive to positive, no sign change. Positive to negative, there's a third sign change. So according to the first step, the positive real zeros, we have two possibilities. It will either be the number of sign changes, which in this case was 3, so we could have 3 positive real zeros, positive real zeros, or we could have less than that by a positive even integer. Even integers are 2, 4, 6, 8. So we could also have 2 less than this, which would be 1. We couldn't have another 2 less because that would give us -1 real zeros, and that doesn't make any sense. So we could have either 3 or 1. Okay, so that's what the first test tells us. The second is going to get us the number of negative real zeros. And for that, what we have to do is we sort of use the original function, but we plug in minus x for x. So what that's going to do is everywhere there is an odd exponent, the sign is going to change. Because what happens with odd exponents, if you plug in a negative, you get a negative times a negative, which is positive, times another negative, which turns it back to negative. Turns it negative. Changes the sign. Whatever it was, it will now be the opposite. Okay? If you have an even number on your exponent, what happens is you get a negative times a negative. That's positive. Positives do not create sign changes. So let's maybe take a quick look at this particular example, and then we'll see how many negative, potential negative zeros there are. Okay, so what we're going to plug in is we're going to look at f of minus x. Okay, so that gives us 3 minus x here to the 7th. Okay, and we subtract 2 minus x to the 5th, and then we're going to subtract minus x to the 4th. See if I can move my tools here so that they're out of the way. And where are we next? Plus 7 negative x squared plus negative x to the first power and finally just enough room to put minus 3. Okay, so what happens here, let's bring this forward. This negative to the 7th is an odd exponent. This is going to result in a negative power here, negative, so think of it as negative 1 times positive 3. We end up with a leading coefficient now of negative 3 x to the 7th. Here's also the 5 is an odd exponent. That's going to result in a negative answer here, and then we get a negative times negative 2. That's going to give us a positive 2x to the 5th. Okay. On this term, we've got a negative x, but it's to the 4th power. That's even, so there's an even number of negatives in here. That results in a positive. A positive times a negative is still negative x to the 4th. Same thing happens with this x squared. It's an even number of negatives, so it results in a positive. Positive times a positive is still positive. You see how there's no sign changes when we have an even exponent. This one here, the negative x to the first power, right? Number 1 is odd, so you have an odd number of negatives. We have one negative. Negative times a positive is a negative. And there's nothing on the 3. There is no variable, so it's just minus 3. There's no sign change there. Okay. Then what we're going to do is now count the number of sign changes. So we're going from negative to positive. There's one sign change. We go from positive to negative. There's another sign change. Negative to positive. There's another sign change. Positive to negative. Another sign change. Oh, there's a lot of them. But a negative to negative, no sign change there. So what we picked up is that there are 4 sign changes, so there's a potential of 4 negative zeros. Real zeros, we'll call them. Yeah, so 4 negative zeros. But again, following the rule here, there's either that number or there's an even integer less, which means there would be 2 less, so there's possibility of 2 of them. So these are just potentials. And then 2 is an even number less than, it could be 0. There could be no negative zeros. So we've got these choices. It's either 4, it's 2, or 0. So we may have to check everything, and because there might not be any. Okay. So we got 4, 2, or 0 as far as negative zeros. As far as the positive zeros are concerned, we have either 3 or 1. So that gives us a potential for possibly having 7 real zeros, right? 3 positive, 4 negative. But we could have less than that. We could have just 1 positive real zero, and we could have 0 negative zeros, which is kind of confusing to say. Don't think about it too long. We could have no negative zeros. Okay. Then we would use the Descartes, we would use the rational, what would we use? We'd use this other theorem to actually figure out what they are. Rational zero theorem. Okay. So let me walk through an example that was presented, and we'll see kind of how far we can get with it, and we'll actually look at finding the possible zeros. Okay, so I'm going to clear all this out. Let's get rid of these guys. Let's just put up an example here and see how far we get. I think I can make better use of my space over here. So let's go with the yellow-green. So let's start off with defining a function. And the one we're going to use is this one, because it turned out to be an interesting example at least. So f of x equals 2x to the 4th, so minus 17 x to the third plus 13 x squared plus 53 x and then plus 21. So we're getting some larger coefficients than maybe we're used to, but we should be just fine with this. Okay, so we'll come over here, and what we first want to do is apply the first rule and count how many sign changes. So this first sign here, it's invisible, but that means it's positive. So there's a positive here, and we go from positive to negative, so there's one sign change. We go from negative to positive, there's another sign change. Positive to positive, no sign change. Positive to positive, no sign change. So we have the potential, I'll put that over here, for two positive zeros, real zeros, or how many? 2 less than 2, so it means we could have 0. We could have none. Zero positive zeros. Okay, so those are our possibilities. To find the negative zeros, what we have to look at is f of minus x. So I'll take a little shortcut. If I put in a negative here, I've got an even integer, so the sign will not change. This is going to be 2x to the fourth. When I put the negative x in here, since I have an odd exponent, I will get a negative result, and a negative times a negative becomes positive. When I put the negative in for this term, I've got an even exponent, so it's not going to change sign. It's going to stay positive. And when I put it in for this term with the 53x, I get a negative to the first power. That's an odd. It will change sign. So this becomes a minus 53x. And of course, the constant term has no place for a variable, so it just remains plus 21. So now I come back and let's count sign changes. So this is positive to positive, no sign change. Positive to positive, no sign change. Positive to negative, here is one sign change. And then we go from negative to positive, another sign change. So for the negatives, so this was positive zeros here. We highlight it this way. And then the negative zeros, we have 2 potential or 0, right? Because 2 for there, and so it's either going to be 2 or only 0. See, 2 sign changes. Good. So now that's sort of the first step. These are the potential, how many zeros there could be. So we could have a potential of 2 positive, 2 negative, or 4. We could have 0 and 0, so we could have no real zeros. How do we go about finding it? Okay, so let's change our color here a little bit. And the possible zeros are going to be the ratio of the factors of the constant term, which in this case is 21, over the factors for the leading coefficient, which is 2. So what are all the factors of 21? Well, 1 times 21, 3 times 7. So we potentially have in the top plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21. In the bottom, we could have plus or minus 1, because the factors of 2 are 1 and 2, or we could have a positive or negative 2. And then the potential zeros are the combinations of all of these. So using the 1 in the denominator, we could have the values of plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21. So that gives us 8 actual different options, depending upon positive or negative. If we have the 2 in the bottom, in the denominator, we end up with potential of plus or minus 1/2, plus or minus 3/2, plus or minus 7/2, and plus or minus 21/2. So then another 8. So there's 16 possibilities here listed. We could just check them all. But in this video, we'll just check a few and I'll leave the rest for you. So how do we check which ones work? Well, we might want to, you could choose to start with either positive or negative. I'm going to start with the positives. I know there's 2 of them. So once I find 2 positives, I could stop. Now, it could be that there's 0, so I might have to keep looking through all of the positive potentials. But if I find 2, I know not to look for a third or a fourth because Descartes' rule tells me there's at most 2. If I find 1, I have to keep going because that's not a potential. There's either 0 or 2. So once I find 1, I know there will be a second one. Okay. How do I find these? Well, we could use synthetic division. Okay, so let's see how we set this up. Okay. So if we want to test, look at my notes here. Okay, yeah, I had a couple examples on my paper, so it was confusing me. So we want to test, let's say, positive 1. We want to see if positive 1 is going to be one of our zeros. And so we do synthetic division. This is the way they teach in the book. So we take the coefficients, -2, and we use the original function. So we come back up to this original function. So positive 2, -17, positive 13, positive 53, and positive 21. We use this for the division. And so then what we do with synthetic division is you just bring the first coefficient down, we get 2. We take 1 times 2, and that goes here. 1 times 2 is 2. We then add these together and get -15. Then we take 1 times -15, and we get -15. We add these terms together, 13 and -15, that gives us a -2. 1 times -2 goes here, it gives us -2. 53 minus 2 is 51. Then we take 1 times 51, and that goes here. And sorry folks, we're not going to get 0. That means we have a remainder, which means 1 doesn't work. 1 is not one of the positive zeros. Now, if you want, you go ahead and put the number here. It doesn't matter though. So 1 doesn't work. So I could cross that off my positive list if I wanted to, but -1 might work. So let's see. So positive 1's gone, but possibly -1 might be there. Okay, let me try another one. And this time, let's try, now as I was doing this, we could try them methodically all the way through, but what I was looking here is, okay, 17, if I get a number here, and 53, that's a pretty big number. Now, I'm thinking of factors, remember I'm multiplying, how can I get something close to 53? Well, that's like 7 times 8, or it's 3 times something bigger, but it's going to lead me to maybe let's try 7, because 7 might work here. And then if I end up with like a 3, I get 3 times 7, I get 21, or I actually want a negative 21 here, so I end up with a 0 remainder. So the fact that I got 21 here is leading me to try both 3 and 7, because when I multiply this last one, if it's the right number, I'll end up with a 0, a 0 remainder, which means it'll work. 21 might also work too, but let's just try, I don't know, anyone, 7. So we again put our synthetic division. Separate it off this way. And we'll just see if this works. So the 2 comes down. That's all that happens. Bring it on down. Oops, but bring down the right number. Bring down the 2. I don't know if that happens to you. That's one of my problems is I so often say the right thing, think the right thing, but then somehow write down the wrong thing. And okay, so fix that. So the 2 comes down. 7 times 2 is 14. Okay, we add them together, and negative 17 positive 14 gives us a negative 3. 7 times negative 3 is going to give us negative 21. And 13 plus negative 21 is going to give us a negative 8. 7 times negative 8 is going to give us a negative 56. When we add these together, we get negative 3, and you might think, oh, bingo, we made it, because 7 times negative 3 is negative 21, which has a remainder of 0. Okay, so what we know is that positive 7 is one of our zeros. So this is cool, because we know we only need to find one more. There is only one more. We don't have to go through all of the positives till we find 0. And my hint is give 3 a try, and you'll see you'll get sort of the same rewarding thing here. On this last term, you'll end up with a negative 21, because 3 times 7, and so the 3 will work as well. What we need to do is do the same thing with the possible negatives. And since there's either 2 or 0, if we find 1, we know there will be another one. Again, I won't go through the details of doing it, but my suggestion is start with negative 1. It could be one of these fractions. That's true. And the fractions actually might not be too bad, because at the beginning the 2 will divide out. But what I would suggest is try the integer values first, because those will probably go much quicker. You might have more difficulty with the fractional ones, but they might be the ones that work. So give them a try. That would give you all the real zeros, and again, we'll get one more here for sure. And I'll tell you, just for if you do this one, you should have 2 more real zeros. One of them I'll give you. This is correct. Okay, and then you'll have to find the other negative 0. So hopefully this is helpful in the process of getting to the answers and finding the actual zeros. Of course, then you could use the other techniques to find the non-real zeros that exist, because, well, if we find 4, remember it's a power of 4, that's the most we can get. So we'll have them all. So again, hopefully this was helpful. Please feel free to send me any questions you come up with, and we'll see what we can do with them. Thanks.